is about W algebras.
So thank you for coming back. So last time, I explained that if you take objects from equivariant coherent, quasi-coherent sheaf on G star, which identify with a full subcategory of Poisson modulo over CG star by taking global section, then we have, if we consider the cohomology with respect to the adjoint action of Q bar. So this cohomology is concentrated in degree 0 and isomorphic to this tensor product. And this defines the exact functor to the category of Poisson modulo over Srodoi slice. And so I didn't really explain for the vanishing statement, but for the exactness statement, we only needed the transversality of the Srodoi slice. And transversality of a Srodoi slice for the jets of Srodoi slice so this also holds for finite jets. So by the same argument, G orbits. So this is a statement for the finite jets, but using the same trick as Raimondo was explaining, we have similar statement for the jet, for the arc space. So we have, if you consider the analogous functor, so now this becomes Poisson vertex algebra module. So this sends M to H dot of M. Now this becomes jets of orbit and group of semi-infinite. And Q0. And this is again concentrated in degree 0, and it's isomorphic to the one replaced, everything is replaced by the jets, infinite jets. So this functor is also exact. The same argument holds. So everything looks quite pleasant. And before going to statement for the vertex algebra, I make a remark. If X affine a Poisson scheme with Hamiltonian G action, then its coordinate ring is, of course, objects here, but this is also is a Poisson algebra, obviously. And so H0 of that cohomology is again Poisson algebra. And so that statement implies that if you take spec, this is a scheme theoretic intersection with X with the Schroeder slice. So similarly, function on the arc space is object here but it also has a structure of Poisson vertex algebra. So in particular, it's a commutative ring. And if you can consider a spectrum of that cohomology, and this is the intersection with scheme theoretic intersection with not really intersection. It's a fiber product of J infinite X and J infinite Schroeder slice over J infinite G star. Okay. And then, so now want to state what happens for the vertex algebra. So a VK module is the same as the category of smooth G hat module of level K. So this is a quite big category. But here we have our favorite category O. It's a category of highest weight module. Category O of G hat of level K. But objects here don't really have action of, so action of G doesn't integrate to the action of G. So we need to restrict to a smaller category, which is Kazran-Lustig full subcategory. So this is consists of object such that the G0, so G acts semi-simply on N. So G is, of course, the subalgebra inside G hat. So if you pick an element, object here, then we have a action of GT integrates the action of this jets of G. So corresponding associate graded is objects which is equivariant, and also the first piece in the filtration is equivariant Poisson module over CG star. So this is the largest abelian full subcategory of OK satisfying this condition. So now the theorem says the following. So this was first proved by Frankel Gatsgory for regular nilpotent element using vanishing result of other vanishing result of myself, and by myself for all cases directly. The statement is that for any element of casuistic full subcategory, we have the vanishing of cohomology. So this functor this is exact. And also, so in the case of M is I forgot to say, so this contains, of course, universal affine vertex algebra, or its simple quotient. And so in the case of M equals to VKG, we saw a very nice commutative diagram. So taking its algebra and taking Zhu's algebra, and all of these things commuted with BRST reduction. And the statement, it's sort of the same is true for any objects of casuistic category. So namely, if you consider Poisson module so there are two ways to construct Poisson module of Sorodo slice. So first you consider Poisson module obtained from the image, and next you can consider Poisson module. First consider Poisson module and take BRST cohomology. And the statement is this naturally isomorphic as Poisson CSF module. So this means in particular, associate scheme of the image of LKG is isomorphic to the scheme theoretic intersection of associate scheme of LKG with a Sorodo slice. Because this is isomorphic to the tensor product with Sorodo slice. So, so this means if you consider as a topological space, so this is just a really intersection of these two varieties. So if you know the associated variety for the simple affine vertex algebra, we know the associated variety of the image. And also, you can, so this generalizes to the whole associated graded, so you can consider associated graded of the image, or you can consider cohomology of the associated graded. And the statement is there isomorphic as Poisson vertex algebra module over function that arc space of jets, slowed slice. So, in particular, a singular support of image. So singular support, I forgot whether unexplained, you explained? So this is just a spec of, so singular support is just a spectrum of GUL of V. And this is isomorphic to the intersection with singular support of GUL of LKG with the arc space of slowed slice. And the last thing, you can consider Zoo's module. So here I have to, so no one really explained Zoo's bimodule. So this is not Zoo's algebra, but Zoo's bimodule. A Frenkel Zoo's bimodule. So, so maybe I should explain. So starting from casualistic category, we get something which lies on equivariant quasi-coherent shapes on G star by taking F1 quotient. And then if you take associated graded, we obtain corresponding arc space analog. And if you, the corresponding object for the algebra setting is not Zoo's module, but Zoo's bimodule, which is in this case Harshchandra bimodule. This is Harshchandra bimodule. So it's a UG bimodule, which is whose action is equivariant with respect to the group. So you can consider a cohomology of Zoo's bimodule, which is Harshchandra bimodule, and then tensor with sorry. So Zoo's, I didn't really explain this one. Zoo's V of Okai. So this is again Zoo's. This is a Zoo's algebra of vertex algebra corresponding to this orbit, but this is just a wide algebra. And then Zoo's algebra of semi-infinite Fock space, which is a usual Clifford algebra. And this becomes Zoo's algebra, Zoo's bimodule over what? Over Zoo's algebra of image of VKG, which is a affine double algebra. So this is a module over bimodule over finite double algebra. And the statement is that this is isomorphic. Again, so in particular, so if you take M to be LKG, this is just a usual Zoo's algebra. So the Zoo's algebra of the image of the cohomology is isomorphic to the, so if I write this as H0 of BRST of Zoo M, so this is Zoo's H0 of Zoo's algebra of LKG. So,
I still don't understand. What is
so this is Zoo's bimodule.
Yeah, what is bimodule?
So to define Zoo's algebra, you quotient out by V over V, which notation with V. But you can do the same for module, something like this, by the same formula. Okay. And then this becomes a bimodule. I see. And this is called Frenkel-Zoo's bimodule. And in the case of Kazan-Lustig, if you take module objects from here, you do get Harshchandra bimodule over enveloping algebra. So this means that if you know Zoo's algebra of simple affine, you can compute Zoo's algebra of the image. So let me make some remark or corollary. So first for, I erased, I just erased. So if the image, image of a simple module. So we are basically interested in the image of a simple module, simple affine vertex algebra. So if this is non-zero, then its associated scheme or associated variety is non-zero, non-empty. But this is intersection, This is intersection of associated variety of LKG with Srodoi slice. But I didn't really explain, but Srodoi slice has contracting cyst action, contracting to the point F. So if you have any point, then if you let cyst act, then you get this point F. So this only possible when this variety contains this point F. And because this is closed and G invariant, this is the same as this orbit is contained in this variety. So 0 is shifted by F because we changed conformal grading. Conformal vector. So if this is the case, this image of simple quotient, simple affine vertex algebra is a quotient of H0 of VKG, which is a universal affine vertex algebra.
So this lower slice is an affine space.
Yeah.
So it obviously has an action of C star, just as an affine space. Get it from G star by shifting from 0, as you say.
Yeah, yeah.
So is this claim here that is this obvious that this C star action coincides with the one that you get from L naught?
Exactly, exactly. Yeah. So, yeah, quotient of this because of the exact statement, because this is a quotient of this, and exact functor sense. So is something wrong?
No, it's just that I didn't see that as obvious.
It's
So I did not understand oh, there are two obvious C star actions, and Tomoyuki is saying that they're clearly the same.
yeah,
Makes sense, it's just that I didn't notice it.
it's if you look, it's designed to be the same. Otherwise, it's not compatible with the differential.
So I can see that in both cases F is a fixed point. I can see that in both F is the fixed point.
What do you mean?
I don't see. Doesn't matter. I'll figure it out.
Okay, so this is a non-zero quotient of universal one. So, but so the unique simple quotient, which I denote by W sub KGF. So this is a simple affine W, is a quotient of this one. Because this is a smallest quotient, so it may be different, but this sits inside, between, so this is a quotient of this. Now, suppose the associated variety of the simple quotient of simple affine is the closure of nilpotent oblique closure of this some element F. Then image of LKG by the Drinfeld-Sokolov reduction with respect to this nilpotent element F is an intersection with this orbit and solid slice. And this is actually intersects with only point F by transversality of the solid slice. So this variety is obviously dimension 0. So this means this image is least vertex algebra, and so is its quotient, WKGF. So as soon as you find nilpotent orbit closure as an associated variety of simple affine vertex algebra, you get this double algebra for free. Which one? This one. So conjecturally, this all coincides. Okay. Yeah. But it's not. Yeah. So now, so recall. Maybe I should start it from this. So this condition sorry. So V LKG, as I explained, so this is quasi-this. If and only if the associated variety is contained in the nilpotent cone. So in this case, if you pick any nilpotent element in this variety, the image is quasi-this because its associated variety in the intersection of LKG with the solid slice. And in the intersection, the coadjoint orbit are exactly the intersection of coadjoint orbit and the solid slice. And because there are only finite many coadjoint orbits, this means the image is quasi-this. And so this means simple affine vertex algebra is quasi-this. So as soon as you find simple affine vertex algebra satisfying this condition, you not only get this double algebra, but you get a family of quasi-this double algebras. And so I do not explain much because it's already used in my previous talk and also in Ant's talk. So if K is admissible, so this means the K plus HK is some positive rational number with some conditions. Then associated variety of simple affine vertex algebra is a closure of some nilpotent orbit, which only depends on the denominator of this number. So this satisfies the assumption in here or here. So immediate corollary is that if K is admissible, then WK GF is least if F is from this orbit and quasi-least if this element is from the closure of this orbit. And in this case, and so in this case, associated variety so I'm repeating the statement, but associated variety of this, so this is conjecturally true, but if so as Michael pointed out, we believe that this equality holds, and if this is the case, then associated variety of simple affine double algebra is intersection with the orbit closure and Srodoi slice. And this is called nilpotent Srodoi slice. And so nilpotent Srodoi slice is quite interesting object, and it's very well known when G is simply laced and F is a subregular nilpotent element. Then in this case, intersection of maybe O is sorry. So if you consider F is a subregular. Subregular. I'm a bit confused. So if you consider the case when OQ equals to the nilpotent orbit closure, then associated variety is of this form. And then this has simple singularity. At this point F of the same type of G. So this is well known by Briss, Kohn, and Srodoi. So we have many examples of quasi-Lis double algebra, and so which generalize this kind of interesting singularity that appears in the associated variety. So maybe it's good to look at what happens for G equals to SL2, which we all know everything. So in this case, associated variety, there are only 3 possibilities for the associated variety for the simpler form. So it is either 0 or whole nilpotent cone or everything. So if it's 0, if and only if k is non-negative integer, so this is a case for integral representation. And this case is when k is admissible, but not integer, and k equals to minus 2, critical level, and else. And when k admissible but not integer, then one can show that the image of Drinfeld-Sokolov reduction of the simple module, so if is just this, is the double algebra, simple double algebra for SL2, and which is a simple Virasoro algebra of central charge 6k plus 1 square over k plus 2. And this is, as I explained, so this, because this is orbit closure of G point F. So this is a least vertex of algebra. And these, so these are exactly so-called minimal series, double Virasoro vertex algebra. So which are rational? Which are rational? Rational by Beilinson, Fagin, Mezu, and Wang. So this is a minimal series Raymond was talking about. So we get minimal series of the Virasoro vertex algebra from the SL2 admissible simple affine vertex algebra. Now, so it makes sense to believe the following statement that if k is admissible, and if f is element from this nilpotent orbit, then by the previous corollary, this is least. But the conjecture is that it's not only, but this is rational. As in the case of the Virasoro minimal model. So this conjecture has a bit long history. So this was conjectured by Frenkel, Katz, and Wakimoto in 1902, soon after double algebra were introduced. So this was only for a principal nilpotent element. And the conjecture was extended for other nilpotent elements by Katz and Wakimoto. And myself. So the thing is that the conjecture of how do I say? So in the work of Frenkel, Katz, Wakimoto, or Katz and Wakimoto, the condition. So this condition was stated in a combinatorial manner. So for instance, for Virasoro minimal series, it's parameterized by P and Q, which is non-negative integer greater than 2 mutually prime, or something like this. So it was stated by, so it's natural to extend to this condition for the for this principal nilpotent element, and so it was stated in that manner, but it turned out that this combinatorial condition can be restated in terms of this geometric condition, and and then we find more example of this of satisfying this condition and extend it to more general setting. And conjecture is now proven. So original conjecture of principal nilpotent element, so this was proved by myself in 16 something. So this case so for this case, we get so-called minimal series, principal double algebras, which extends minimal series of the Virasoro algebra. And for G equals to SL3 for minimal nilpotent element, so this case was also done myself, and SL4 for F subregular. So it's done by Krutihilincho. And SL4, P4, and subregular. This was done by Justin, as she explained in the seminar. And for all type A for all cases, and type ADE is subregular. So this was done by myself and Jethro, with Jethro. I think it's going to be published in a journal this year. And finally, all cases in full generality by McRae in the recent preprint. So now this conjecture is proved. However, this is not the end of rationality problem of double algebra, because there are rational lease or quasi-lease double algebras outside admissible level. So this was first discovered by Kawasetsu. And myself and Ann. And we don't really know now how to classify these lease or double algebras. But maybe I'd like to conjecture that if associated variety of simple affine is closure of some nilpotent orbit, then WK df is automatically this, but it's also rational. So it's very important to classify simple affine vertex algebra satisfying this condition. So, so it's important to classify quasi-lease simple affine vertex algebras. And also, there are, I believe, I have some evidence for that, but I have not really proved it, to find and classify lease, but non-rational double algebras. And I'd like to also remark the following. So, if F is a nilpotent element, then we usually consider corresponding the component group. So a component group of the centralizer of F. So this is a connected component of the centralizer of F. So this is a finite group of a deck transformation of the equivariant covering of the orbit of F And this naturally appears, this plays an important role in the representation theory of while group or Hecke algebra. And so this naturally acts on the set of simple WKGF modules if this one is least. So it permutes the set of simple module. And because it comes from the automorphism group of double algebra, it also acts on the modular tensor category corresponding to the double algebra if so WK is rational. So this makes representation theory or is interesting and both interesting and difficult. But so far, so McRae's result is very general, and he didn't really talk about the set of simple modules. But almost other cases have only trivial action of the component group. So we don't really see this, but except for the work of Justin. So in the work of Justin, you really see the non-trivial action of the component group. And in this paper, we found many interesting, not many, a few interesting modular tensor categories. So because there are many nilpotent elements, there should be many interesting modular tensor categories equipped with the action of this component group. So it would be interesting to describe such a modular tensor categories. So because of the, so there are still problems for the least case, but somehow it's quite now satisfactory because of this result of McRae. But representation theory of more general quasi-least double algebra is now wide open. So not very little is known about representation theory. But we know or expected by physicists that it's occur in 4D 2D duality when a level is boundary admissible. So it's expected have interesting connection to other mathematics. For example, conjecturally expected have interesting connection with, for example, affine Springer fiber. So this is a work of Pen, Yang. So something very interesting is going on. Now, any questions so far? So statement is the number of simple modules is counted, described in terms of affine simple, affine spring of fiber, for instance. Okay, so now I'd like to talk about general representation theory. So general means, so when you talk about the representation theory of affine Katsumuni algebra, you are not only interested in, you are interested not only integral representation, but also all irreducible highest weight representation. So how to describe, for example, character of irreducible representation of double algebras. So we have a nice functor from a casuistic category to the module of a double algebra, which is exact. But problem is that we not all simple highest weight representation of double algebra Shan, pen Shan, sorry, Shan. Sorry, so I should write Shan. Not all simple highest appear as the image of this functor. So if you want to know the representation of double algebra using such a functor, Pension, yeah. No H? So you're saying this? Strange. Yeah, so we need to enlarge the category to understand general highest weight representation of double algebras. And so this is most present for a minimal nilpotent element. So in general, representation theory of double algebra becomes more complicated when as a dimension of the nilpotent orbit grow. And this has the smallest dimension. So you expect that this representation theory of the minimum double algebra is the simplest. And in this case, this is very present. So we have the vanishing of cohomology for all objects in category O, not only casuistic category. So this functor extends to the exact functor from the category O to the double algebras. double algebra modules. And if you consider image of Varma module, so this is Varma module of affine Katsumudi, then this is isomorphic to a Varma module of WK G if theta. And if you send simple quotient, so this is a simple quotient of Varma module, then this is a simple over 0, and simple if lambda alpha 0 chech is not non-negative integer. So this is k minus lambda of theta. So if else. And moreover, all the simple highest weight representation of WK G if theta appears in this way. So I should comment. So this theorem determines the character of all irreducible highest weight representation of minimal double algebra for all non-critical level. So this is because so we know by Kashiwara and Tanisaki we know the character of simple highest weight representation of affine Katsumudi can be written in terms of Kazandristic polynomial. I don't really specify this, but so this is an integer expressed by a Kazandristic polynomial. So we know the character of a simple module of affine Katsumudi. But then exactness of the functor means that this functor defines a map between the characters. So we can, this formula implies immediately formula of this type. And you can choose, if you choose lambda to be properly, you get all simple module on the left-hand side. And this is a Varma module of a double algebra. So this has a simple character formula. So this describes a character of all highest weight representation. And this Kazandrisky polynomial is associated with the affine wide group of the G. So in particular, if you go back to this explains the fact that the character of irreducible highest weight representation of Virasoro algebra can be written in terms of affine while group of SL2. And another remark is that the theorem is valid for the superalgebras. So you can also define W algebra for the superalgebras. And as long as W algebra is defined, so this is a case when it's a basic classical. So basic classical means inner product is, I forgot, even. Yeah, so I forgot, but so it's valid for almost meaning. So except for the queer and strangely superalgebra, you can extend this theorem to this superalgebra setting, and where almost all superconformal algebra appear. As double algebra. So this was the result of Katz and Rowan. So they show that the essentially all superconformal algebra can be obtained as double algebra for the minimal nilpotent element. So if you know the character of irreducible highest weight representation of affine D superalgebra, you get character of all superconformal algebra for free, but unfortunately we don't know the character of the affine D superalgebras. So maybe I can another application. So I erase? Maybe I just erase. So there was a criterion that this simple module is non-zero or not. So if you apply this criterion for a simple affine vertex algebra, so this is non-zero if and only if k is non-negative integer. Right? So this was a condition. But this has as I explained before, this is the same as associated variety contains a minimal nilpotent orbit. So this shows the Don Mason's theorem that if associated variety is 0, or so if LKG is least, then this is 0, so k must be non-negative integer. So this was stated by Anne as Don Mason's result, and she explained the proof of the other direction. But you can use double algebra to show the opposite direction, which is a different proof of, from the Don Mason's result. So this is a case for the minimal nilpotent element. And other case is not as nice as a minimal nilpotent element. So unfortunately, so this functor is only right exact. So you can show the vanishing of positive degree but no negative degree. Four are general. If, so in particular, if is a principal nilpotent element. But you can fix this problem at least for principal nilpotent element. So you can modify modified BRST reduced cohomology, which I denote by H maybe minus, it's called minus reduction functor. So this is defined by Frankel, Katsuwa, Kimoto. And which enjoys the following property. So maybe functor. So which is a functor from OK to the double algebra module for the principal nilpotent element, which M2H minus N0, such that the same property holds, such that first for we have the vanishing of cohomology. So the functor is exact, and H0 of gamma is a gamma, and H0 of simple is simple over 0. The simple if top part is isomorphic to gamma of G. It may feel a bit strange, but so we impose that the top or lowest part is the generic simple module. So this does not mean at all that this is a generic, and is, and all a simple highest weight representation appear in this way. So from this, of course, we get character of all irreducible representation. All character, all irreducible highest weight representation of a principal double algebra. So similar result holds for all nilpotent elements in type A. So as a result, we know the character of all ordinary irreducible highest representation of double algebra of type A. But for other types, we don't have such a result. And the main difficulty is this action of component group. And now there's another proof of this statement. Using categorical Beilinson Bernstein localization theorem, type theorem by, so this was very recent paper by Dillon and Sam Raskin. So we have now a geometric proof of this statement. I mean, geometric proof of the character formula. So I still have 5 minutes. Maybe I comment a little bit about other realization of double algebras. So the theory of BRST reduction is nice as long as you talk about double algebras only. But double algebra appear in many areas of mathematics, and often it's not clear how to relate the algebra they appear and with the one defined by BRST reduction. So we sometimes need other realization of double algebras. So one realization is so-called screening operator. So this is a case for the principal nilpotent element. Oh, so let's take F to be principal nilpotent element. Then it's or the result of constant. Then so the sheet algebra is a slowly slice for the principal nilpotent element. But this has other realization, namely, if you consider restriction map from here to here, and you restrict this restriction to the gene invariant polynomial, this is isomorphic. And this is so, but by Chevalier restriction theorem, so the ring of gene invariant polynomial is the same as ring of while group invariant. So this can be expressed in terms of a intersection of kernel of S1 minus 1, where S1 is the simple reflection. And kernel of S1 minus 1. So, if it's because while group is generated by a simple reflection, if all simple reflection acts by one, then it's while group invariant. And this picture has been upgraded to the double algebra setting. So we first upgrade dual of Cartan to the vertex algebra. So this will be the vertex subalgebra generated by Cartan subalgebra. So this is Heisenberg vertex algebra. This is Heisenberg. Then if you take associated scheme, you recover this one. Then the theorem of Fagin-Frankel is that there exists a natural vertex algebra embedding from principal double algebra to little bit shifted level Heisenberg vertex algebra. And the image of gamma can be described similarly. So this is intersection of kernel of some operator called a screening operator, which is written in terms of some vertex operator for a generic parameter. So I don't have time to explain what is screening operator, but we have similar description. And so this result was generalized by master thesis of Naoki. He's not there. So you have similar generalization of the Fagin-Frankel theorem for all double algebra. So all double algebra can be written in terms of kernel of screening operator in some much easier vertex algebras. So maybe my time is up, so maybe I should stop here. it's not really compatible with associative variety. It's nicer in the sense that it captures simple module, but it's not compatible with associative variety. I should say it's not compatible with the vertex algebra structure. And as a last speaker, I'd like to thank Desro. So thank you, Desro. And Raimondo.